Stanford University.
All right. This evening, I wanted to get started on talking about particle mechanics in the special theory of relativity. How particles move, notions of momentum, energy. We will get to E equals mc squared, and that sort of thing. The next time, or maybe even tonight a little bit, we might even get move past that if we get finished with it and start to talk about classical field theory. Let me just do one thing on the blackboard that we will need recurrently and over for various purposes, mostly for purposes of showing that the relativistic formulas that we write down have the limit of the non-relativistic formulas that we may have written down, that we did write down 2 quarters ago in classical mechanics. We are going to want to show that when objects move slowly compared to the speed of light, that the newfangled relativistic theory of particle motion and particle mechanics reduces to the old-fangled Newtonian. Okay, for that we're going to need to make approximations which become better and better for slower and slower velocities. And in particular, the thing that we're going to have to approximate. Now, I know you all know this, but I'm going to do it just for completeness on the blackboard. We have this quantity which recurs over and over, 1 minus v squared, square root of 1 minus v squared. It really means square root of 1 minus v squared over c squared. If we measure the velocity in units of the speed of light, then it's just 1 minus v squared. But we remember that v represents a fraction of the speed of light of the object which is moving with velocity v. So typically it's very small. And we just want to write down how we approximate this for small velocities, in particular how we approximate it to order velocity squared. This is just an example of the binomial theorem. I'll write it down once and for all. We'll use it a couple of times tonight, and I assume everybody knows it. The binomial theorem says that 1 plus a small number epsilon, doesn't matter if it's small, but 1 plus a small number epsilon to a power p, where p can be anything, as a matter of fact. It can be positive, negative, imaginary, complex, doesn't matter, that this can be expanded in powers of epsilon, a Taylor series if you like. If you don't know Taylor series, we just expand it in powers of epsilon. For epsilon equals 0, it's just given by 1. And then the next term is p times epsilon. Now I'm not going to prove this. This is the standard binomial theorem. And the next term, everybody remember the next term? P times, p choose 2, which is the same as p times p minus 1 over 2 factorial. 2 factorial is incidentally just 2, times epsilon squared. And then it keeps going like that. I'll write the next one, and you can write all the ones after it. It's a homework assignment to write out all the infinite number of them. What? Yeah, pi. Over 3 factorial, epsilon cubed, and so forth. If epsilon is not too big, then this series will converge. And the meaning of saying it converges is that each term is significantly smaller than the previous in such a way that that it's a good approximation to terminate the series after an appropriate number of terms, where appropriate depends on just how much precision you want. But in particular, if epsilon is really very small, it's usually the case that the first term is the most important one. Of course, it's the 0th term, which of course is the most important one. but the zeroth term is awfully boring here. We're going to find for the various applications that the zeroth order term, the 1, is just too boring to be relevant to us. And it's the first order term here which is important. So let's terminate the series at that point. Of course, it does break down if epsilon is not too small, but that's the... all right. So supposing we want to expand 1 minus v squared, square root of 1 minus v squared, where epsilon is now, we're now using epsilon equals minus v squared. In other words, 1 plus epsilon is the same as 1 minus v squared. And the power p, in this case, is equal to 1/2. Square root of a quantity is that quantity to the 1/2 power. And so this becomes 1 plus epsilon, which is 1 plus p epsilon, which is 1 plus 1/2. That's the p. And then epsilon is minus v squared, which is the same as 1 minus v squared over 2. So that's a pretty damn good approximation for small velocities, in particular for non-relativistic velocities, to the square root of 1 minus v squared is just 1 minus v squared over 2. That's where a lot of 2's in classical physics come from if thought about as the limit of relativistic physics. Most of the 2's, and I'll show you some examples, come from here. And I'll show you some examples as we go along. The other example that we will need will be 1 divided by the same thing. This case is the same as 1 minus v squared to the power minus 1/2. The only difference relative to what we just did above is that p is minus 1/2. That has the effect of changing the sign here so that this becomes 1 plus v squared over 2. Two signs have conspired to cancel each other. The sign from the half up in the exponent and the minus v squared here give us 1 plus v squared over 2. All right, so that is just by way of setting up a little piece of calculational mathematics that we'll use in various situations. All right, now we're going to be interested in particles. Now, a particle can be anything that holds itself together. It doesn't have to be an elementary particle. It could be the sun. It could be a box of chocolate. It could be a cookie. No cookie. It could be anything. And when you think about the location of whatever it happens to be, it could be a donut. Let's take the case of a donut. What we mean by the position of the object is generally the center of mass position. When we talk about the mechanics of the motion of particles, we're speaking really about the mechanics of the center of mass of an object. In the case of a donut, the center of mass is where there is nothing, but that's okay. We know where the center of mass is. And motion, according to the center of mass, is governed, for example, by Newtonian mechanics of F equals ma. Momentum is mass times velocity. Does it matter whether it's an elementary particle or a donut or cookie? No. Its momentum is its total mass times its velocity. Its kinetic energy is 1/2 mv squared in Newtonian physics. That's the energy of motion. Does it have any other energy? If it's a donut, does a donut have any other energy besides 1/2 mv squared? Yeah, calories, exactly. It has all the internal chemical energy and that sort of stuff that's inside the donut. That part of the energy does not depend on its overall motion, on its state of motion. It's a constant. It's a constant with respect to how fast the object is moving. So you can say that the energy of a moving donut is 1/2 mv squared plus the internal energy, and the internal energy doesn't depend on the state of motion. Okay, so those are just some reminders about classical mechanics. Another reminder about classical mechanics is to go back and read the classical mechanics book, where you will find things like the principle of least action, which we will use tonight, Lagrangians, canonical momenta, and all that stuff, and we're going to use them. So very quickly review in your head now the previous quarter of classical mechanics. The important idea about the principle of least action was the idea of a trajectory in space-time. Not just a trajectory in space, but a trajectory in space-time that if you plot position of a system, it could stand, x could stand for a one-dimensional coordinate, it could stand for a three-dimensional coordinate. In fact, it could even stand for the coordinates of a large number of particles, and we can just call it space, or coordinate space. Vertically, we plot time, and the trajectory of a system between two instants is a curve that goes from one point to another curve. And we can call it a world line. If it's a particle, if it's a single particle, we call it a world line. We call it the world line of the particle. Now, this concept is just as good a concept in non-relativistic physics as it is in relativistic physics, but it takes a certain primacy in relativity because of the connection between space and time, that space and time can morph into each other by a Lorentz transformation. We tend to focus more on the idea of space-time. The trajectory of a particle is time-like. Now, what do I mean by time-like? Let's define the notion of time-like. Begin with just 2 points. Begin with any pair of points in space-time, and think of the separation of the coordinates, the difference between the coordinates of the 2 points. The difference of the coordinates, now I'm speaking about space and time coordinates, we can call them delta t and delta x. I discussed for a couple of times already the notion of the invariant proper time between the 2 points, and we wrote that as delta t squared minus delta x squared is equal to delta tau squared, where delta tau itself, the square root of this quantity, is the proper time connecting those 2 points. Now, this quantity can be positive, this quantity which I've written delta tau squared, it can clearly be positive or negative. It is positive if the separation between these points is such that the t interval is larger than the spatial distance between them. In other words, if the interval is like so, if the spatial distance is less than the time distance, in that case, delta tau squared is positive, and the interval between these 2 points is called time-like. It's got more time in it than it's got space in it. When an interval is time-like, you can always find a Lorentz frame of reference. You can always transform to a frame of reference where the 2 points are at the same position, where it hasn't moved. In fact, you simply go to the frame of reference where this line is at rest. There always exists such a frame of reference. And so if 2 points in space-time are time-like separated relative to each other, you can always move in such a way that they wind up being at the same point in space, that they haven't moved relative to each other. Okay, that's one case. The other case is where delta x is bigger than delta t. In that case, the separation has more space interval than time interval. Looks like this, let's say. It's at less than 45 degrees relative to the horizontal. Incidentally, I should say right now, when I'm thinking about four-dimensional space-time, 3 coordinates of space, 1 coordinate of time, what delta x stands for is the 3 components of the vector delta x, and delta x squared means the sums of the squares of those 3 components, delta x squared plus delta y squared plus delta z squared. Okay. I suppose we could, if we liked, if we wanted to be fancy, we would put a little arrow over here to indicate that it's a 3-vector, that delta x is a 3-vector. All right, now if the 3-vector delta x is bigger than delta t, then the interval becomes space-like. Right? Space-like intervals are, as I said, are more space than they are time. And in this case, you cannot find a reference frame in which the 2 points are at the same position in space. What you can do is you can find a reference frame in which they are at the same time. You can always find, so that means that there's no invariant significance to one end being later than the other. You can always find a frame of reference in which the 2 points are at exactly the same time, and even worse, I've drawn this so that point B, let's call it B and A, point B appears to be later than point A, but there exists a reference frame. This you can work out. It's very easy to work out. You can find a reference frame in which point B is earlier than point A. So there's no invariant significance for points which are separated by space-like interval. There is no invariant significance to which one occurred first, one being later than the other, or being simultaneous. This is the relativity of simultaneity. Okay. Particles move on time-like trajectories. Everywhere along the motion of a particle, if we break the trajectory up into little intervals, every little piece of that trajectory is time-like. That's just a statement that particles can't, nothing can move faster than the speed of light. We've already seen how frustrating it can be to try to get something to move faster than the speed of light. You try to compile up a whole bunch of velocities, each of which is 9/10 the speed of light. You know, stationary observer shoots out something with 9/10 the speed of light. The moving thing shoots out something else with velocity 9/10 the speed of light. The something else shoots out a third thing 9/10 the speed of light. You never get anywhere. It's like Zeno's paradox. You just get closer and closer to the speed of light without ever getting there. And so it seems like a reasonable hypothesis that nothing ever goes faster than the speed of light. And that's a good thing, because it would get very confusing if we said a particle goes from A to B, but we can't make sense out of which one is earlier, the starting point of the particle or the end point of the particle. Would get us very confused. We get into all sorts of questions of time travel and so forth. But the physical fact is nothing, including a photon, can move faster than the speed of light. And I would generalize that and say that information is carried by physical systems. Signals that signal information from one place to another can also not propagate faster than the speed of light. We can take that as a postulate, but if it were otherwise, we'd get into some very paradoxical and inconsistent situations. All right, so that's the notion of time-like and space-like, the notion of the world line of a system, and the world line of a system is made up out of small time-like intervals. Now let's focus on one of those time-like intervals. Let's redraw it over here. Here's one of the time-like intervals. I will imagine in your head that it's a small interval, because eventually we're going to let that interval get smaller and smaller. I don't think we talked about, did we talk about relativistic four velocity? We didn't do it. We didn't do it in any detail. All right. All right, so along the trajectory, the particle moves from one point to another point with a separation delta x, but delta x is a four-dimensional delta x. It consists of a delta t and a delta of the 3 other coordinates, which I'll of course call delta with an arrow above them. That's delta x mu. Sometimes I will call these spatial delta x's. Sometimes we'll call them delta xi. When you see an I, it just runs over space. When you see a mu, it runs over all 4 coordinates of space. This is an interval along the trajectory here. Has 4 components to it, and it defines a delta tau between the 2 endpoints of the interval. Delta tau is equal to the square root of delta t squared minus delta x squared. Incidentally, just once or twice every so often, let's put in the speed of light just to remember where it goes. T has units of time, x has units of space. To make this thing, since this is called proper time, let's assume that it has units of time. This one's okay. It has the same unit as the left-hand side, but this one is not okay. It has units of length. This one has units of time. Where do we put the speed of light? Divide by c squared. Right. I'll do it now and then, every so often. Do it once more over here. And then stop doing it because it gets annoying. Now we have the concept of velocity. Now, basic ordinary velocity is the derivative of x with respect to t. But there's a notion of 4-dimensional velocity. It is a 4-vector. It transforms as a 4-vector. Delta x mu transforms as a 4-vector. Delta tau is an invariant. It doesn't transform. Every observer, no matter how they're moving, ascribes the same delta tau but different delta x mu's to this interval. The velocity, ordinary velocity, let's call it v with a vector here. The ordinary velocity is, its components are simply the xi by dt, or the limits. In the limit that the delta x's get small, it just becomes the limit of delta xi divided by delta t. That's a 3-dimensional notion of velocity. There is, and of course, this also has this should be written this way, or vi is equal to dxi by dt. All right, that's one notion of velocity. A more invariant relativistic notion of velocity is, instead of using t down here, refer the separation of coordinates to the proper time instead of to the coordinate, instead of the frame-dependent ordinary time. That gives rise to something called 4 velocity. It doesn't have 3 components. It has 4 components. So it has a mu up here. The mu stands for the 4 components. Incidentally, mu runs from 0 to 3. 0 is the time component. This is equal to dx mu by not d tau, but not dt, but d tau. So there are 4 of them, and they constitute what is called the 4 velocity, the 4-dimensional analog of the velocity. First question is, what is the connection between the 4 velocity and the ordinary velocity? So let's work that out. Non-relativistically, of course, there are only 3 components of the velocity, so that must mean something funny happens to one of the components here, and we'll see what happens. All right, let's start with dx sub I by dt. Let's start with v sub I. That's equal to dxi by dt, but let's write it as dxi by d tau divided by dt. That's a triviality. I've just divided and multiplied by d tau. But it's useful. Sorry. Yes, this is correct. All right, now dxi by d tau, what is that? That's u sub I. U sub I, where I now am in particular concentrating on the space components of u, times dt by d tau by dt. We'll come back to d tau by dt in a moment. In fact, we're going to come back to it right now. But let's consider the, before we go ahead, let's consider exactly this quantity u naught. What is u naught? U naught is the fourth component of this relativistic velocity. And what it is it's dt by d tau. That's exactly what it is. dt by d tau. The fourth component, or the zeroth component, I should say, of x is just t. Where is it? T. And u naught is just dt by d tau. d tau by dt is just the inverse of this. Right? So we're interested in figuring out what d tau by dt is. Let's figure out what d tau by dt is. D tau is the square root of 1, nope, it's the square root of dt squared minus dx squared. That's just rewriting this thing here, but with differential notation. dt squared by times dx squared, and this means all three components, the sums of the squares of all three components. Let's take out of the square root dt. Let's take it outside the square root of t. In other words, factor it off this stuff. And then we get in here 1 minus dx squared by dt squared. Or just dt times the square root of 1 minus v squared. So what do we know? We know that d tau by dt is equal to the square root of 1 minus v squared. That's what this 1 minus v squared is, or the square root of 1 minus v squared. It's the rate of change of proper time relative to ordinary time. If v is close, if v is small by comparison with the speed of light, if it's close to 0, then this is close to 1. In other words, in the non-relativistic limit, dt by d tau is just 1. There's no difference between tau and t. Okay? If the object is moving with close to the speed of light, there can be a large difference. All right, let's see, where were we? All right, so what we want from here is this equation over here. I've crowded too many equations together. I was working on this. Here's where I was working. All right, so first, I'm making a little bit of a mess out of this, a mess of the blackboard in any case. All right, first of all, this is equal to dt by d tau. What is dt by d tau? d tau by dt is square root of 1 minus v squared. What is dt by d tau? It's 1 over that, right? So u naught, whatever it is 1 divided by the square root of 1 minus v squared. It's a thing which non-relativistically just goes to 1. In the non-relativistic limit, where v is much smaller than the speed of light, this is just 1. That's why we never think about it. We never think about dt by d tau because tau is t and d tau by dt is just 1. Good, all right. On the other hand, relativistically we worry about it. What about here? V sub I is u sub I d tau by dt. But d tau by dt is again just, which way is it? d tau by dt is square root of 1 minus v squared. Divided by, let's see. Yeah. V sub I is dx d tau dt. Looks like it's multiplied. Why does that surprise me? No, it doesn't surprise me. That's correct. That's correct. So now we can assemble together what is the meaning of the forward velocity in terms of the normal velocity. First of all, u naught, the time component of the forward velocity, is just 1 over the square root of 1 minus v squared. What about the space component? U sub I, that we read off from here, that's equal to v sub I divided by that same square root of 1 minus v squared. All right, so this is the basic computation you would do to find the components of forward velocity. Again, if we're talking about the non-relativistic limit where v is very close to 0, then the square root is trivial, and u sub I and v sub I, the two notions of velocity, are the same. As you get up closer and closer to the speed of light, it looks like u sub I is much bigger than v sub I. Is that right? Yeah, u sub I is much bigger than v sub I. Or v sub I is much smaller than u sub I. Okay, this is the notion of forward velocity. This is the notion of forward velocity. And everywhere along the trajectory of a particle, the particle is characterized by a position. You can add in the time at which you're characterizing it. So that's a 4-vector of position. And also a 4-vector of velocity. Now, the 4-vector of velocity doesn't really have 4 independent components. It only has 3 independent components. Let's go through why that's true. Let's take the Okay, I'll explain very quickly why it doesn't have 4 independent components. There is a relationship between the 3 components of spatial velocity of u sub I and u sub naught. And it's just a relationship that u sub I, let's call it u squared, which happens to be v squared over square root of v squared over 1 minus v squared. That's the space component squared is v squared divided by 1 minus v squared. If I
in a way, it seems like you can just see it from the definition of u0.
Yes, we can. Yes, we can, but I'm halfway through it, so let's finish it. Let's take u naught squared minus this thing here. All right, so that's a minus sign here plus 1 over square root of 1 minus v squared. I'm making this more complicated than it is. The answer is that the right, not square root, just 1 minus v squared. Oh boy. What's the right-hand side? 1. 1 minus v squared over 1 minus v squared. 1. So all 4 velocities, no matter how fast the particle is moving or not moving, the square of the square, or the difference of the squares of components, time component and space component, is always equal to 1. Right? It's always equal to 1, and that's why there are not 4 independent components of the forward velocity. Only 3 independent components of the forward velocity. They're related by a single relationship like this. Otherwise, they're independent.
Could you also say that, could you conceptualize it by saying that it's because you're differentiating with respect to one of the components?
Say it again.
Can you alternatively conceptualize the dependency by saying that it's because you're differentiating with respect to one of the components?
Yeah, sure. Yeah. There's an easier way to, I said this badly. Let's go through a very simple version of it. All right, delta tau squared is equal to delta t squared minus delta x squared. Okay. Boy, did I make a mess over there. Let's just divide both sides of this by delta tau squared. We get 1 is equal to delta t squared over delta tau squared minus delta x squared over delta tau squared. delta t by delta tau, that's u naught. So the first term here is just u naught squared, and the other one is u vector squared. Okay, so that's all that went on here. A complicated way to say this. All right. But let's go back now to the world line. Here's a world line. It's characterized by a 4 velocity and a 4 vector, only one redundancy, and that's that the 4 components of u are not completely independent. We want to know what law governs the motion. Let's take a free particle, one with no forces on it. What law governs its motion? And the law that we're going to abstract from a quarter's worth of classical mechanics is the principle of least action. All right, the principle of least action, the only thing new is that the action is going to have, we want our laws of physics to be the same in every reference frame. That means we should try to cast them in terms of quantities which are the same in every reference frame. If we have a principle that says that in going from here to here, the particle goes along a trajectory which minimizes or maximizes, minimizes some quantity called the action, we are doing good business if we make sure that that action doesn't depend on which frame of reference it's evaluated in. We would like the action to be something which is the same in every reference frame. We know of only one, and that's one fact. The action should be invariant. And the other thing that we've learned from experience is the action should be built up incrementally as a sum over the trajectory of little infinitesimal pieces for each segment of the trajectory. That we can abstract from classical mechanics, action being a sum or an integral, better yet, an integral over the trajectory, and the thing of which it is an integral should be a quantity which is the same in every reference frame. There's really only one thing that is invariant in going from a position to a displaced position, and it is the proper time along the trajectory. The proper time from here to here is an invariant, meaning to say that all observers, no matter what velocity they're moving with, will not agree on the delta x's, but they will agree on the delta tau. So a good guess, and it's the right guess, a right guess for the action is the sum, we'll convert that to an integral in a moment, of all the little delta taus from one end of the trajectory to another end of the trajectory. All the delta taus, that is the action. Not quite, not quite. And that action has to be minimized, holding the endpoints fixed. Remember your classical mechanics. The action principle, you hold the initial and the final configuration fixed, and you search for the trajectory that minimizes or makes stationary the action between the two endpoints of the trajectory. All right, so you wiggle around the path until you find the path of least action. Okay. Since the action is composed out of invariants, everybody will agree that a given path minimizes the action. All right, so that's our principle. Add them up. Okay, so what does that mean? That means we have a freedom, incidentally. We have a freedom. We could multiply the action by a number, any number. It won't make any difference. Why not? Because if a thing is stationary with respect to changes of the trajectory, if I multiply it by 10 or 7 or minus 15, it will still be stationary. Of course, if I multiply it by a negative number, I will turn a maximum to a minimum, but I won't change the fact that that trajectory makes the action stationary. Yeah?
What happened to energy?
Why are you getting ahead of the game? We start with action. Energy we derive. We will do that. We will do that. Before the evening is over, we will discuss why we didn't start with energy. But the answer is it's not invariant. It's not even invariant in ordinary Newtonian physics. The energy of a particle is not independent of its state of motion. So if you see a particle standing still and I see the particle moving, we ascribe a different kinetic energy to it. So it's not an invariant concept. It's a good idea to start our discussion of particle motion by talking about invariance that everybody agrees upon, and in that way make sure that our laws of physics are the same in every reference frame. Okay, so yeah.
Could you state again why a relativistic invariant is a good choice for action, or a good guess for action?
It's a good guess. It's a good guess simply because it's the same for every observer, no matter how they're moving. That's what proper time was. Proper time was the particular combination of delta x's and delta t's between 2 points that everybody will agree on the value of it. Okay? It's the thing which is invariant under Lorentz transformations. Right? If we want our laws of physics to be invariant, it would be a good idea to base them on quantities which all observers say have the same value for. So, for example, if I just say, it's analogous to the following. This is entirely analogous to the following idea. Supposing I am interested in the shortest distance between 2 points on the blackboard, what do I do? If I'm interested in the shortest distance between 2 points, obviously I search for the shortest distance. But I search for the curve which has the shortest distance between the 2 points. Now, might we find that we get different answers in different coordinate systems, that coordinate system or that coordinate system or whatever? No, of course we won't. And the reason is distance in the Euclidean plane is invariant with respect to rotations of coordinates. In particular, if we think of the distance from one point to another along the curve to be a sum of a lot of little incremental distances, and everybody agrees on the incremental distances, then the curve that we get will not depend on the coordinate system that we use to evaluate it. Why? It's an invariant concept, the shortest distance between 2 points. What we do then is we add up all the little Euclidean distances here, and we're doing exactly the same kind of thing, adding up all the little proper times along the trajectory. In fact, the formulas are almost identical apart from the sign. All right, now, we have a freedom. We could multiply this action by a number.
Excuse me.
Yeah.
You may have said this, but I don't remember it. We arrived at proper time at being delta t squared minus delta x squared.
Square root of that. Square root of it.
Squared.
Yeah.
Was there a reason? Is there a reason why you inherently choose the positive square root as opposed to the negative square root?
Oh, we will always choose the positive square root. Yeah. Yeah, proper time is by its very definition a positive quantity. It's the time read along the clock from the past to the future. And we could use the negative root. If we used the negative root everywhere, it would simply change the sign of the action. That's okay. What would happen if you change the sign of the action? It would not change the equations of motion at all. Instead of saying we were looking for the minimum of the action, we might say we were looking for the maximum of the action. But remember, to minimize a function or to maximize it, exactly the same equation. You just say it's stationary. So it doesn't matter whether you take the action and multiply it by a number, including the possibility of a negative number. It won't change the trajectories if the rule is the trajectories should make stationary the action. Stationary means it could be a minimum or a maximum.
I guess also, if you had a coordinate system in which the x-coordinate didn't change, then if you chose the positive square root, then the proper time is the same as the time.
Yes. Yes, that's true. That is true. All right, and I'm going to put in one more little sign, one more little change. I'm going to put a minus sign in here. Now, as I said, multiplying by minus m changes nothing. It's a convention. It's a complete convention But the convention was established not by Einstein when he was doing relativistic mechanics, but long before Einstein, by people who had no idea what the special theory of relativity was, but who had some prejudices about the way classical Newtonian mechanics works. So we're going to come back why this minus m is there. We'll come back. It's for the purpose of matching on to non-relativistic formulas. It would not change anything if we didn't put it there, but in order to match with non-relativistic formulas, we'll put a minus m there for the time being. Okay, so let's take that to be the action. And now what we do is the interval is, the trajectory has already been imagined to be broken up into intervals. And now we move the points around in space and time and look for the trajectory which minimizes, or makes I'll say minimize, which minimizes the action, and that will be the true trajectory. That's the principle of least action. But before we do that, let's convert this to an integral. Let's convert this by taking the limit in which the differential, in which these finite differences here are replaced by differentials. So this will become then minus m times the integral of d tau along the trajectory. The integral, and I'll explain exactly what this means in a moment, the integral is sum of little infinitesimal d taus from one place to another. There's a reason why the integral is written by this curly symbol here. You know what the curly symbol means? Sum. Right? And delta tau just becomes d tau from one end of the trajectory to the other, from the initial end to the other end. And now we can write down a formula. D tau is equal to the square root of 1 minus dt squared minus dx squared. And dx squared means dx squared plus dy squared plus dz squared. Now this is a funny thing, an integral with a d tau and underneath a thing in a square root there. I bet you've never seen an integral like that. Maybe you have, where the differential things are underneath a square root. But it's easy to fix. It's easy to make it look more standard. Factor out a dt. Factor out a dt and put the dt on the outside. That means under the square root, we have to divide by dt squared. And this just becomes 1. And what about dx by dt? That's the good old-fashioned velocity squared. So this becomes 1 minus velocity squared, or 1 minus xi dot squared. Xi dot squared means x dot squared plus y dot squared plus z dot squared. All right. I won't bother writing the sum, and I won't bother writing x, y, and z. It's just x sub I dot, and dot now means derivative with respect to ordinary time. Derivative with respect to ordinary time. So by factoring out a dt, I converted this to something a little more recognizable than it might have been before. It's an integral of something that depends on the velocity. Remember about the ordinary principle of least action. In the ordinary principle of least action, for an element, for a particle, for example, the action is an integral over a quantity called what? The Lagrangian. And the Lagrangian depends on what? Positions and velocities. What about for the case where there are no forces? Then it only depends on the velocity, not the positions. And here's what we got. We have something like that here. We have that the action is minus m times the integral of 1 minus the square of the velocity from the initial starting point, let's call it A to B. So we have a Lagrangian now. And now we can just take off and do all the things that we would do with a Lagrangian. Let's write what the Lagrangian is. The Lagrangian is minus m, which I say is a convention, minus m over here, times the square root of 1 minus, now I'll write it, x dot squared plus y dot squared plus z dot squared. it's not as simple as the usual the Lagrangian that Lagrange first wrote down. The Lagrangian that what did Lagrange write down? He just wrote down for the Lagrangian the kinetic energy. He didn't even know, I don't even know if he knew it was energy. He wrote down for the Lagrangian just 1/2 mx dot squared. Okay. That's nice and simple. Lagrangian of Lagrange, L sub L. That was just m x dot squared over 2, 1/2 mv squared, where x dot squared does mean x dot squared plus y dot squared plus z dot squared. This is the Lagrangian Lagrange would have written down. This is the Lagrangian that a relativistic version of Lagrange would have written down. What's the connection between them? Well, the first connection between them, and the most important for our purposes right now, well, before I say that, what is the value of this Lagrangian? The value of this Lagrangian is that it encapsulates the motion of a free particle in a way that is independent or that is the same for every reference frame. It is guaranteed because this quantity of the action is independent of reference frame, making it stationary, you'll get the same answer in every frame. So this is the translation of that to Lagrangian language. Okay. First, let's ask what this is approximately like, not approximately, but what it's like in the limit where the velocities are much smaller than 1, 1 being the speed of light. So this is 1 minus m square root of 1 minus v squared, velocity squared. For that, we go back to the good old binomial theorem. The binomial theorem tells us that the square root of 1 minus v squared is approximately equal, this is approximately equal to minus m times 1 plus v squared over 2. So first of all, there is a contribution which is just minus m. It doesn't depend on anything. It doesn't depend on position. It doesn't depend on velocity. It's just a number. What does adding a number to the Lagrangian do? Does nothing. Adding a number to a Lagrangian does nothing because the trajectory, the action of the trajectory, comparing different trajectories, the constant piece here doesn't depend on the trajectory, doesn't depend on the x, doesn't depend on the velocity, plays no role at all. So it's not important to us. Right? The important piece, do I have to, I'm sorry. Minus, right? 1 minus v squared over 2. All right, so apart from the constant piece, the piece with the juice in it, the piece with juice in it is plus mv squared over 2. Minus m plus mv squared over 2. In other words, it's just the Lagrangian of Lagrange. In this way, we can be certain that the laws of motion that we derive in this way will, in the limit of small velocity, be the same as good old Laplace, Lagrangian, Newton, and so forth. So far, we haven't put in anything that resembles a potential energy or a force law. So far, we're simply working with a free particle. Okay. So that's a good thing. Now, next concept. I'm not going to work out the equations of motion. I will tell you right now, the equations of motion have the brilliant ability to simply make this particle move on a straight line with constant velocity. We'll see that. But the equations of motion are not the interesting things for this evening's lecture. The interesting thing is to identify the notions of momentum and energy. That's where we want to go. We want to understand where the relativistic formulas for momentum and energy come from. Okay? They're not quite the same as the non-relativistic formulas. So let's go through them. Momentum and energy are important because they're conserved. If we account for all the particles in the universe, or at least all the particles in a closed system, they may be interacting with forces and this and that, but the net momentum is conserved. What was that a consequence of? Do you remember what that's a consequence of? Translation invariance. All right, so translation invariance, and translation invariance is true here. We're actually in a special case of Lagrangian mechanics. Everything we said about Lagrangian mechanics, Lagrangians, Hamiltonians, conservation laws, it all applies here. It's just that the Lagrangian is a little bit strange. It has a square root of 1 minus x dot square plus y dot square plus z dot square. But other than that, the rules of the game are the rules of Lagrangian, Hamiltonian, whatever we derived previously, and we can use it. All right, so the first question then is, what is the meaning of momentum? It will be conserved. It will be conserved because this Lagrangian is translation invariant. It only depends on the velocities. It does not depend on position. It's translation invariant. The momentum will be conserved as a consequence of everything we learned the first quarter. Okay, so I would like to identify, for example, P sub x, the x component of momentum. So we go back, we open up our book on classical mechanics, and we go back to the definition of momentum, not the definition which began by saying momentum is equal to mv, but the definition which came from the Lagrangian point of view, and that was, anybody remember the definition of momentum? In terms of the Lagrangian? Everybody have it at their fingertips?
Was it partial L, partial Q dot?
Yeah. The derivative of Lagrangian with respect to the component of velocity. Derivative of Lagrangian with respect to x dot. I won't bother redoing classical mechanics in front of your eyes here. It's a little bit too late for that. At this point, thing to do between now and next week is to review this. I should have told you last week. P sub x is partial of L with respect to x dot. Same thing for P sub y, P sub z, and so forth. So let's apply that. Lagrangian is minus m times the square root of this thing here. All right, so this is going to be, first of all, is a minus m. Then there's a derivative of this square root with respect to x dot. All right, what do you get when you take the derivative of a square root? You get 1 over a square root. One over a square root of everything inside the square root, which happens to be 1 minus v squared. Yes, there's a half. Thank you. There's a half there. Now we have to take the derivative of the thing inside the square root with respect to x dot. All right? That's going to give us a minus from here. So there's another minus sign, plus, and then the derivative of this thing with respect to x dot, which is twice x dot. So that will eat up the 2 in the denominator. And it will put an x dot here. Or mv sub x divided by the square root of 1 minus the total velocity squared. Well, we've seen this before, have we not? Right here. V sub I, in this case v sub x, divided by square root of 1 minus v squared is just u sub x. So what do we get? We get p sub x, here it is, p sub x is nothing but the mass, not times the ordinary velocity, but by the ordinary velocity divided by square root of 1 minus v squared, which is u sub x. The relativistic 4 velocity times the mass is equal to the x component of momentum. Likewise, for the y component and so forth and so on, the y component, p sub y, is equal to m u sub y, and likewise for z.
M is rest mass.
M is the rest mass. M is mass. Okay, let's talk about a convention. The use of the term mass, rest mass, and all that stuff. There's an old convention and a new convention. The new convention is older than I am. More or less. Nobody that I know who does physics uses the term rest mass anymore. Rest mass is an anachronism. That's the word, anachronism. In other words, right. It's an anachronism. The only place where it's ever used is in undergraduate textbooks. Undergraduate textbooks cannot seem to get their head around the idea that the mass of a particle is a tag that goes with a particle which characterizes the particle and not the motion of the particle. The mass of an electron, if you look up mass of an electron, you won't get something that's different if the electron is moving or stationary. You will simply get whatever it happens to be. I don't remember the mass of the electron in kilograms, but it's some small number. So the way that mass is used in modern language is it's a number that goes with the particle, but it is exactly what used to be called the rest mass. What used to be called the rest mass is now just called mass. What used to be called mass is what? Energy. Energy divided by the speed of light squared or something. We use the term energy for the thing which characterizes the moving object, and the energy at rest we just call the mass. Now, there's the speed of light factor. That's just a conversion factor, and we'll come to it. All right, so when we talk about the mass of a particle, we mean what used to be called the rest mass. From now on, I will never use the term rest mass. I will always use the term mass, meaning the energy at rest. Okay, good. Right, it's an important distinction. I normally don't even think in the language of rest mass, so I didn't mention it, but it was good that Warren brought it up so that we don't get confused. Okay. Now let's talk for a moment about 4 vectors. 4 vectors are the things like delta x and delta t. Supposing I have a 4 vector. In this case, it would simply represent a little interval. That's the 4 vector of displacement, I guess you would call it. The 4 vector of displacement that has a delta t and a delta x. Now, supposing I told you that delta x, as opposed to delta t, that delta x was equal to 0, could that be an invariant characterization of this interval? What happens to delta x when you Lorentz transform? It changes, right? In particular, it'll pick up a little bit of delta t. So it cannot be an invariant description of this vector. A vector with delta x equals 0 would be a vertical vector. But in some other frame of reference that we're moving past the stationary axis, the same vector would be tilted. In other words, if you were moving past it, the beginning and the end point would be separated by some delta x. So the statement that delta x is equal to 0, that might have some significance to a particular frame of reference, but it can't possibly be an invariant distinction. What about the statement that delta x and delta t are both equal to 0, or all 4 of them, not just delta x and delta t, but delta y and delta z? Is that an invariant statement? All components of this vector are equal to 0, of this 4-dimensional vector are equal to 0. Well, if you think about the way things transform, a delta x, when it transforms, will pick up a little bit of delta t. Delta t will pick up a little bit of delta x. But if delta t and delta x is 0 in one reference frame, then it will be 0 in every reference frame. So saying that a vector, a 4 vector in particular, is 0, the whole thing, all components of it, that's an invariant statement. To say some specific component, or even a specific subset of components, less than all of them, is equal to 0, that is not an invariant statement. The same is true of the 4 velocity. The 4 velocity, here are its components. Is it an invariant statement to say that u sub I is equal to 0? I meaning for just the space components. No, it isn't, because if you, what it means to say that u sub I is equal to 0 is just that you're in a frame of reference where the particle happens to be stationary. Change frame of reference, u sub I will not be 0. Okay? So in general, if you want to express invariant statements, you want those statements to be about all components of a 4 vector. A 4 vector means a thing like delta x or u. You want it to be a statement which is true for all the components. You want it to be a full-fledged vector statement, full-fledged 4 vector statement. Okay, let's come to the concept of momentum conservation. Momentum conservation. We've so far identified 3 components of momentum. Only 3 components. Those 3 components of momentum happen to be proportional to the components of 4 velocity. They happen to become proportional to the components of 4 velocity, but that's incidental for a moment. The important thing is that momentum is conserved. If I have a collection of particles and we add them all up, the initial momentum must be equal to the final momentum. Now that's a vector statement. That's a vector statement that the 3 components of momentum, and let's label them this way, initial must equal the total initial momentum must equal the total final momentum, or we can subtract and just write the law of momentum conservation says that this is equal to 0. Initial momentum minus final momentum is equal to 0. This in itself is a vector equation. Is it an invariant vector equation? If it's true in one frame, is it necessarily true in another frame? Not unless we can make an equivalent assertion about some 4th component. If there is a 4th component that turns the momentum into a 4 vector, and then we say all 4 components are conserved, then it becomes an invariant statement. Okay. Then it becomes an invariant. It's only an invariant statement if we can identify a 4th component and say that the 4th component is also conserved. A 4th component such that the 3 components together with the 4th component add up to a 4 vector. Well, it's pretty darn clear what the 4th component of this thing has to be, huh? What must the 4th component be? It must be m times u0. We have 3 components. If we didn't have the m there, we would have 3 components of the 4 velocity, and the 4th component of the 4th velocity would just be the thing which fills out the full 4 vector. So, question, is there a significance to mu sub naught, whatever it is? We can give it a name. We can call it p sub naught. We can give it a name. Is there a significance to it, and is it something that we already recognize as something which ought to be conserved? And of course the answer is yes. There is a 4th thing which is conserved for particle mechanics. It's energy. So it's natural to ask the question, is this the energy? Is this 4th component of 4 momentum nothing but the energy of the particle? Well, how do we decide that? How do we decide what the energy is? Anybody got a clue about how to decide what the energy is? Ah, look at the Hamiltonian, right. And that's the only way. That's the only systematic procedure. Look at the Hamiltonian. So the next step is to figure out the Hamiltonian. We're going to erase some of the blackboard here and go to the Hamiltonian. In a sense, from the point of view of relativity, all the work that we did in the same quarter was just to set ourselves up for this kind of problem. Okay? All right. So let's go to the Hamiltonian. I know that not all of us remember what the Hamiltonian is, so I will remind you. The Hamiltonian is given in terms of the Lagrangian. Again, I don't expect you to remember it, but I do expect you to be able to look it up and remind yourself where it came from, why this was an important quantity. It's a conserved quantity. It's an important quantity. I will write it down for you. It's the sum over all the coordinates, of a system of the velocity associated with that coordinate. I sometimes put the indices upstairs and sometimes I put them downstairs. Pay no attention to where I put them at the moment. And what does it multiply? Remember? The momentum associated with that same direction. I'll put that one upstairs just for variety. And then, but that's not finished. What else is there? Minus the Lagrangian. That's the Hamiltonian. As I said, if you want a systematic way to think about mechanics where we don't just make up stuff as we go along, we fall back on the basic principles of mechanics, a la Lagrange, Hamilton, and so forth. Okay, so now we can write it down. We now know what it is. Let me write the Lagrangian over here, and the p's. What is p sub I? P sub I is equal to m x sub I dot divided by square root of 1 minus v squared. That is the same as m u sub I, but I'm not going to use it that way. I'm just going to use it the way it is here. P sub I is that. And the Lagrangian is minus m square root of 1 minus v squared, where that means vx squared plus vy squared plus vc squared. That's the Lagrangian. We have everything we need now to calculate the Hamiltonian, or what is essentially the energy. Okay, so we have then summation over I, x sub I dot times p sub I, that's m x sub I dot squared over, I think, square root of 1 minus v squared. Is that right? That's the first term here. The x sub I dot squared picks up 1 x sub I dot from here, 1 x sub I dot from here. The mass is over here. And now minus the Lagrangian. So minus the Lagrangian is plus m square root of 1 minus v squared. Looks like a bit of a mess, but it is not. It is simple. First of all, x sub I dot squared. That's just the total velocity squared. X dot squared plus y dot squared plus z dot squared. That's what I call v squared. So the first term here is just not even a sum anymore. It's just m v squared over square root 1 minus v squared. Then we have to add plus m times the square root in the numerator. How are we going to add a thing with a square root in the numerator to a thing with a square root in the denominator? Well, we'll put everything in the denominator. So we have to multiply and divide by square root of 1 minus v squared. That gives us in the numerator 1 minus v squared, and then square root of 1 minus v squared in the denominator. There we are. Okay, now it doesn't look so fearsome anymore, because we notice immediately that mv squared over here cancels mv squared over here, and the whole thing is m upon square root of 1 minus v squared. All right, that's the Hamiltonian. So let's add to the momentum a fourth component here, P naught, which is M. And do you recognize what this thing is? This is U naught. So indeed, we find that apart from a possible, yeah.
When you wrote down the Hamiltonian, that was the classical non-relativistic chemistry.
No. This formula for the Hamiltonian is extremely general. All systems that we've ever studied, this is the formula. That was the general formula for any Lagrangian, any action principle. We derived the conservation of H in very, very general grounds. Right? Depending on what you put depending on what you put in for the Lagrangian, it might be non-relativistic physics. It could be any number of things. Good. All right. So now we're in business. The conservation of momentum becomes the conservation of 4 momentum. Conservation of x momentum, y momentum, z momentum, and the conservation of energy. Before we go on, we should figure out what this new concept of energy has to do with the old concept of energy. How different is it than the energy that we've already established? Okay, so let's... The one thing that we're going to have to be careful about is the factors of speed of light. They are conventions, largely. They're conventions. If the energy defined in one way is conserved, it won't make any difference to its conservation if we, in order to make it match with units, if we multiply it by the speed of light or something. Conservation is conservation, and we will probably have to do that. Okay, let's look at mu naught. That is m over the square root of 1 minus v squared. That's what we're calling the energy of the particle. Now, of course, if we want to restore some, well, before we restore units, let's use the binomial theorem. Let's use the binomial theorem to approximate this. Here it is. Here's the binomial theorem for 1 divided by square root of 1 minus v squared, and it gives us 1 plus v squared over 2. All right, so this becomes m plus m v squared over 2. This, of course, is completely recognizable again. It is just the ordinary Newtonian kinetic energy. Had Newton known about energy, this would have been what he would have written down for kinetic energy. It is what kinetic wrote down. I have no idea who first thought of this as energy, but somebody did. What about this term over here? Well, first of all, this equation is not dimensionally consistent. Not dimensionally consistent. Here you have an m, and here you have an m times a velocity squared. To make it dimensionally consistent, all we have to do, we can do it in a number of ways, right, to make it dimensionally consistent, but to give it units of energy, we're thinking that it's the energy, to give it units of energy, this already has units of energy. It's just a good old kinetic energy. In order to give this term units of energy, we have to multiply it by some power of the speed of light. What power of the speed of light? Well, we already know this thing is missing 2 powers of a velocity compared to this one. So what's it going to be? It's going to be mc squared. All right, I will just write that this is the energy. So here we see, coming out of the basic principles of mechanics, the conservation of a quantity which, when it's evaluated for a system at rest, is just mc squared. Okay? For a system at rest, its energy is related to its inertial mass, by mc squared. How do we know that this is the inertial mass? Well, it's the inertial mass because it enters into the energy the same old way that inertial mass entered into the old energy. It enters into momentum, at least for slow velocities, in the same way that the inertial mass entered in here. And so this must be the inertial mass times c squared. That's the origin of, Einstein had another way to think about it. He asked himself, in a collision of objects of various kinds, given, he worked a little bit differently. He didn't know about Noether's theorem. He had to work from the ground up, so to speak. He talked about collisions of objects. Objects come together, break up and scatter and go flying off. And he said, look, I know that the momentum is conserved. What do I have to think of as the energy in order that the energy and momentum together would form a complex that would be conserved in any frame of reference? Right. We've short-circuited that and found the formula for the energy by standard methods. Okay, so that's the origin of E equals mc squared. It doesn't apply only to a particle. It applies to any object that can be identified as a closed object, that its energy, when the object is at rest. Now, what does the object being at rest mean? Inside here, there are lots of molecules moving around like crazy. So in that sense, this object is not at rest. On the other hand, its center of mass is at rest if I hold it at rest. What we mean by the velocity here is the velocity of the center of mass. And what's left over when you set the center of mass velocity to 0 is the rest energy. The rest energy is related to the mass by a factor of speed of light. Another way to say that is that the speed of light is just a conversion factor from one way of defining energy to another. It's just a conversion factor.
It sounds silly, but you want to make the dimension consistent, so you multiply by c squared.
If I would have, yeah.
You could have multiplied by c squared over 10 million, or a lot of different things.
No. It has to reduce to this when c is 1.
Okay.
Right. Good point. Good point. That's right. On purely dimensional grounds, we never could have deduced that this would be 1 here. But on the grounds that it has to reduce to this when c is equal to 1, we say there's only one thing we could do with it.
So that 1 in the binomial expansion is important.
Oh, yes. Absolutely. Absolutely.
There are higher order terms missing, right?
Yes, there are higher order terms, and they are simply very, very small when the velocity is...
Care about them.
Well, I mean, for some purposes we might care about them, but the leading piece for slow, we could evaluate them and we could see how small they are for a baseball moving at 90 miles an hour, and believe me, they would be really, really small.
What's the right physical way to think of those higher order terms? Corrections to the kinetic energy?
Yeah, they're corrections to everything. Everything gets corrections. Those corrections are quite significant when the object is moving close to the speed of light. In fact, I mean, they become huge. Let's just think about it for a minute. If I were to plug in the speed of light here, well, this would get pretty darn big, but it wouldn't get any bigger than this. But it's perfectly finite. On the other hand, if I plug it into this formula, v goes to 1. The kinetic energy of an object moving with close to the speed of light becomes infinite. That's another way to see that you can never get up, because it would take an infinite energy to get up to the speed of light. Also an infinite momentum. These u's also are v's divided by square root of 1 minus v squared. So as you push the particle faster and faster, its momentum and its energy increase and explode, diverge, become infinite when the velocity becomes the speed of light. That means it would take an infinite force to accelerate a particle to a speed of light, and infinite forces are simply not part of nature.
I've lost track of one thing here. What is the thing that now becomes invariant as a result of adding that fourth component?
The conservation law. Right. Of form momentum. Conservation of form momentum. That's exactly right. Okay. Yeah.
Recently, a earlier statement that really was only 3 dependent variables because of u naught, u squared minus u naught squared being wrong.
Yes, we're going to come back to that in a minute. Right, right. That's just a statement that that energy is determined in terms of momentum.
If you have two particles with opposite velocities, does the mass of the combined system is it greater than the sum of the two masses?
Typically, yes, of course. If you wanted the mass of the combined system, by that I mean the energy of the combined system when the combined system is at rest. Now, what does it mean the combined system is at rest? It means exactly what you said, that the two objects might be moving in opposite directions. Then the energy is definitely larger than the sum of their masses.
So, and in this convention, the rest mass is greater than.
The rest mass, all right, now we have to be careful about definitions. Some things are simply purely definitions. Some people might react at this point, well, what I mean by the rest mass is simply the sums of the rest mass of two particles. That is not a very good invariant concept at all. Another person might mean, no, I don't mean that. What I mean is think of the thing as a unit and discuss its energy in the frame of reference where its total momentum is equal to 0. That would be what we would call the center of mass frame or the rest frame of the combined system. Now, since all ordinary systems are made up out of particles that are moving hither and thither all over the place, a invariant concept is the energy of a system in a reference frame where its momentum is 0. If we call that the mass, then the mass of the composite system in your case, in your particular case, would be greater than the sums of the two masses. If there were forces, particularly attractive forces, it might be less than, but that's another case.
What does the mass term do when you include it in the phase of a wave function?
It gives an e to the I m squared c squared, mc squared, times time. Right.
So I've got one. I mean, I have trouble forming this into a question, but I mean, the way we got this expression was just a lot of abstract mathematics, Lagrange's, Hamiltonians, that sort of thing.
Let's not call it abstract. Let's call it systematic.
Whatever.
No, I mean,
this MC squared term is very significant, right? I
Indeed.
mean, it describes things like an atomic bomb, for example. I mean,
yeah.
it's...
Yeah, the thing that's conserved is the total energy, not the individual masses of particles. So let's talk about an example. Oh, before I talk about the example, let me first take a little digression into massless particles. Massless particles are a little bit strange. Here's the energy over here, m divided by 1 minus v squared. Now, what's the velocity of a massless particle? 1. Okay, we're in trouble. Well, maybe the trouble is not too bad. The numerator is 0 and the denominator is 0. It doesn't tell us what the answer is, but at least it tells us at worst it's 0 over 0. That's better than 1 over 0. Okay, right? Maybe not a lot, but it's a little better than 1 over 0. All right. It doesn't seem like such a good idea to try to think of massless particles in terms of the energy of massless particles in terms of their velocity, since all massless particles move with exactly the same velocity. Can they have different energy if they all move with the same velocity? Well, yes, they can, and the reason is because 0 over 0 is not determined. Thinking about massless particles, it is not good to think about them or to distinguish them by their velocity. All their velocities are the same. Okay? We have to think about it differently. The way to think about massless particles, and in fact, we can think about any particle this way, but to think about massless particles in particular, is to think of the energy as a function of the momentum instead of the velocity. Okay? We even do that quite often in ordinary mechanics when we write the energy of a particle, kinetic energy. It is 1/2 mv squared. Okay, that's one way of writing it. But another way to write it is momentum squared over twice the mass. I'm talking now not about relativistic mechanics, just old-fashioned mechanics. we write the energy in terms of we write the energy in terms of the momentum. That's another way, an alternative way to express the energy. Okay. What happens if we do the same thing in relativity? Can we find the expression for the energy of a particle in terms of its momentum? Well, there's a very simple trick. The simple trick is just to use the fact that u0 squared minus ux squared, let's add them all in, minus uy squared minus uz squared. That's right, you said it, uz squared is equal to 1. We worked out that before. And now I'm going to set C, for the moment I'm going to set C equal to 1 again, C equal 1. All right, if I multiply, let's see, the components of momentum, all 4 of them, are the same as the components of 4 velocity except for a factor of mass. So what I want to do is multiply this equation by m squared. M squared, m squared, m squared, m squared. And then this is the square of p0 squared, but p0 is just the energy. So this becomes the square of the energy minus, and each one of these is the square of the corresponding component of momentum. E squared minus p squared, I forgot to multiply this side by m squared. E squared minus p squared equals m squared. In terms of the 4 velocity, it's u0 squared minus u vector squared equals 1. In terms of the corresponding components of the 4 momentum, energy and momentum, it's e squared minus p squared equals m squared. Or I can write that as e squared, or E, equals square root of p squared plus m squared. I moved the p squared over to the right-hand side and took the square root. Let's put back the speeds of light. I'm going to leave this as an exercise for you. I'll tell you what the answer is. This is the square root of p squared becomes p squared c squared, and m squared becomes m squared c to the 4th. Check that out. It's just an exercise in getting your units straight. And there it is. It's energy in terms of momentum, square of momentum, and the mass. Now, from this formula, we can immediately take the limit that the mass goes to 0. We had trouble thinking about a photon in terms of velocity, but we have no trouble in thinking about photons in terms of this formula. What does it say? It says,
Yeah, right sum becomes 0.
Yeah, that's right. Energy becomes equal to the square root of the square of the momentum times the speed of light, which is just the speed of light times the magnitude of the momentum. Let's call it magnitude of momentum. Square root of p squared is just the length of the momentum vector. Energy for a massless particle is simply the magnitude of the momentum vector, but in order to keep the units correct, you have to multiply by the speed of light. This is true for photons. It's approximately true for neutrinos. Neutrinos have a tiny little bit of mass. It's true for gravitons. It is not true for particles which move significantly slower than the speed of light. All right, now that we know how to express the energy of a massless particle, we could solve the following equation, the following problem. Let's take a particle. I'm going to give this particle a name. It's called positronium. Happens to be an electron and a positron in orbit around each other, but it's not important what we call it. Just It's not important what it is, it's important what we call it. We'll call it positronium. It's an electrically neutral particle, and it has a mass. Its mass is approximately the mass of 2 electrons. But I don't care whether you call it 2 electrons or not. It's a little bit, is it more than 2 electrons or less than 2 electrons? Less than. And why is it less than? It's bound. Yeah, it's right. It's got a little bit of kinetic energy, so that makes it a little bit more than 2 electrons, but it has even more negative potential energy. All right. So whatever the positronium particle is, it doesn't matter what it's made of. It's simply an electrically neutral particle with a mass of, I don't know, I'm not going to ask you to look up the mass of the electron. We don't, yes, let me ask you to look up the mass of the electron. Yeah, it's 0.51 MeV, but it's something in joules. I was hoping somebody would give it to me in joules.
9 times 10 to the minus 31.
What is it?
9.1 times 10 to the minus 31.
Is that true? I don't remember. I have no idea. I mean, I know it's 9.1 times 10. That's the electron mass. All right. So 9.1, that's 1.8, 9.1, blah, 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 some number of joules. That's the positronium. So there's positronium. And if you leave positronium around for a while, positronium will decay. What will it decay into? It will make 2 photons. 2 photons will go flying off. Positronium will disappear. The 2 photons will just go off. In other words, you've made electromagnetic energy out of them. You've made just plain old electromagnetic energy out of the positronium. Positronium disappears and becomes, in its place, 2 photons going off, separating from each other. Can you calculate what the mass, not the mass, what the energy and momentum of those 2 photons are? All right, so let's go through the exercise. This is something which would not make any sense at all in non-relativistic physics. In non-relativistic physics, the sums of the masses of particles are always unchanged. Chemical reactions happen, some chemicals turn into other chemicals and so forth, but if you weigh the system, if you weigh the mass of the system, the masses, the sums of the ordinary masses never change. Okay, that's non-relativistic physics. Here the sums of the ordinary masses is changing. This has a mass of whatever it was in joules. This has a mass of whatever it is in kilograms. And each of these is massless. The photons has no mass. So the sums, the numerical sums of the masses of particles is not conserved. Not if this process happens, and this process does happen. But the right rule is not that the sums of masses is conserved. It's that the energy and the momentum is conserved. So the first question is, what is the momentum? Let's do momentum conservation first. Let's assume that the positronium atom, the positronium particle, is at rest in our frame of reference. If it's not at rest in your frame of reference, just move your butt and get into the frame in which it is at rest. Okay? Right. Get into the frame in which it is at rest. So it's at rest. What's its momentum if it's at rest? 0. So the total momentum of the system to begin with is 0. Now it decays to 2 photons. The first conclusion is the photons must go off back to back in opposite directions. If they don't go off in opposite directions, it's quite clear the total momentum will not be 0. So they have to go off in opposite directions. They will go off in opposite directions, and they must have exactly equal, back to back, equal and opposite momentum. Why? The initial thing had 0 momentum. The final thing has 0 momentum. All right, so that means that this particle goes off with a momentum p, and this particle goes off with a momentum minus p. Good. Now let's use energy conservation. The energy of the initial positronium atom is its mass, whatever its mass is, times the speed of light squared. This is not the mass of the electron, not exactly. Very, very close to it, but not exactly. A little bit less than twice the mass of an electron. But it is the mass of the positronium atom. So you get out your spring balance, or whatever it is, your scale. You put a positronium atom on it, and you weigh it. And that's the mass of the positronium atom. And when it's at rest, in the rest frame, it has an energy equal to mc squared. That has to equal the energy of the resulting 2 photons going off. So this has to equal the energy of the 2 photons. The energy of the 2 photons is the same because they have the same magnitude for the momentum, and it's just equal to twice the speed of light times the momentum, times the absolute value of the momentum, p. So that tells us what the absolute value of the momentum has to be. It's mc over 2. That's the momentum of each one of the photons. That's the simplest example of calculating a relativity decay and calculating what happens. This is the momentum of the photons that go out. We could convert this using a little bit of quantum reasoning. We could convert this to a wavelength for the photons going out. If we use the connection between wavelength and momentum that we learned last quarter, we could convert this to a statement about the wavelength of the photons. It's very small. I mean, it's much, much smaller than optical. So this is the mechanism by which a mass turns into energy. Of course, the mass was always energy, but it was in this frozen form of rest energy of the positronium molecule. And when the positronium atom decays, it results in 2 photons going out. The 2 photons collide with the atmosphere, with everything else, and heat it up. They can be absorbed by electrons, generate electrical currents, and so forth and so on. So it becomes, the energy gets converted from this frozen form of rest mass into a dynamical, useful form of electromagnetic energy. Yeah.
How is spin conserved?
Well, if the atom to begin with has 0 angular momentum, and these guys are going off back to back, they better have opposite angular momentum.
So if the electron and positron are lined up together, it won't decay?
No, don't decay. It'll always decay. It'll always decay. It's always, you have enough freedom. You have enough freedom in the photon angular momentum to make it go. Yeah.
Can you explain why massless particles have to go at the speed of light, or is that too far outside this class?
Well, let's put it this way. In order to have a finite energy, in order to have a finite, well-defined energy, if V goes to 1, the denominator goes to 0, the mass in the numerator had better also be 0. That's all.
You said it'd be the same for all massless particles. If the resulting particles were gravitons, what would the initial particles be?
Some fraction of the time, the positronium atom, for example, will decay into a pair of gravitons. Now, that percentage of the time is 10 to the minus, I don't know, some large number. But some percentage of the time, the electrically neutral positronium atom will decay to just a pair of photons. Yeah. Gravitons. As I said, don't look for it in the laboratory. Yeah.
That decay has to be instantaneous because of time dilation also?
Instantaneous means what? What does it mean that the
if you have, let's say, the two photons emitted, the positronium decays into those. Because of time dilation, they're instantly going at the speed of light. That means that their internal clock is 0. That means that it's close to an instantaneous process also, right?
Well, let's see. So what experimental question would you ask? You could detect the photons in some sort of chamber that leaves tracks, and you could trace the 2 photons back, and you would discover that they both come together at exactly the place where the positronium was, and so that you could say, look, if they decayed, if the decay was peculiar and the positronium decayed, first producing one photon that went out to here, and then later creating the other photon which only went out to here, they're both moving with the speed of light, and you trace them back, they would appear to come from somewhere over here. That doesn't happen. If you trace back the trajectories of the photon as they leave tracks in a chamber or something like that, they will come back and intersect at exactly where the initial positronium atom was. I'm not sure if that's the question you're asking, but I think that's the only thing I can make out of it.
Your board there is hiding the equation I want to refer to.
What's that? Oh. Yeah.
I understand you concluded that E squared minus P squared equals M squared from that equation up above.
Right.
And it looks like that equation is saying that U naught squared minus U x squared minus U y squared minus U z squared is 1?
Yes.
Why is that?
Oh, we went through that, but I'll go through it again. I'll go through it again for you. We already had two versions of it, but one of them was garbled. And I guess an ungarbled one just cancels out a garbled one and leaves no explanation. All right. So do you remember this formula? Delta tau squared is equal to delta t squared minus delta x squared? Okay. Ah, oh, here it is right over here. Right, here it is. Right, good. Yes, Kevin?
So U naught
Yes,
is dt d tau.
that's
Or
correct.
delta t delta tau.
Right.
What does that mean about energy? Does that tell us anything about energy?
It doesn't strike any deep chord in me. You know, I know it's true. Does it really ring something powerful? Only in the sense, well, let's see, you want to dt d tau. Nothing really visceral in that. Because at rest, dt d tau is 1. In motion, it's not 1. And it's telling you how the energy changes as a function of velocity. But nothing more than that. Yeah. Yes?
It's more of a common sense question, but when the positronium, when it decays, and you have two photons going off, and the net momentum is 0,
Yeah.
is it through quantum effects possible for the net momentum to be a teeny tiny little bit different than 0?
Not if momentum is conserved. Well, in a laboratory situation, in any laboratory situation, of course, there are contaminating effects. Even if nothing more, the presence of some tiny stray field, magnetic or electric field or something, could corrupt the thing and lead to a slightly different answer. Remember, the rule is momentum is conserved for a truly isolated system. A truly isolated system means that you've accounted for everything in the system and nothing else is interacting with it. Then the momentum of that system is conserved. Now, if your laboratory is sufficiently isolated and the region of space is cold enough that there are no particles bombarding and so forth and so on, the positronium together with the and the photons constitute an almost closed system. But you know, it's really not completely closed. There's if nothing else, there's gravitational forces between the Earth and the particles. They're completely negligible, but they're not zero. So yeah, there are contaminating influences.
I mean, theoretically, like the uncertainty principle, that if you know the
That doesn't affect it. Momentum is conserved.
then where it is
The better you know the momentum, and in particular, the better you know the relationship between the momentum, it may be that, that you have less information about the relative positions. But that's a small effect, and for our purposes tonight, I want to separate quantum mechanics from classical. But it's a real question. Right.
Your formula for energy was just an approximation.
Well, there was an this was an well, this is not an approximation.
That's right.
This, well, let's see, where is it? I lost it. Yeah.
The equation E equals m plus mv squared over 2.
That was an approximation.
So the non-approximation is E equals m over the square root of 1 minus v squared.
That's right. This is.
Put the C in that equation.
Oh, okay. Let's do that. Okay. Over here. All right. So we begin with E equals. What do we want to start? M divided by square root of 1 minus v squared?
Right.
So we look at the units, and in a minute, well, right now, a 1 and a v squared have different units. The only way to make v squared have the same units as 1 is divided by c squared. There's no other way. Now the 1 minus v squared over c squared is dimensionally consistent. However, the whole formula is not. The left-hand side is energy. The right-hand side now has units of a mass. Mass and energy don't quite have the same units. They're related by the square of a velocity. We know that the units of energy are equal to the units of mass times the units of a velocity, let's put v, squared. An example would be kinetic energy is 1/2 mv squared. We know that's consistent. All right? So it tells us that we have to provide the square of a velocity here, and that tells us that the c squared has to go over here.
Right, and then if you set b equal to 0, you get the
That's right. Then you get just plain mc squared. Right.
For the positronium experiment, the electron-positron pair has to decay into 2 photons simultaneously in all frames.
Has to decay into 2 photons and then what?
Simultaneously in all frames of reference.
Yeah. Yeah. It decay.
The distance between the electron and the positron.
Well, that's a hard thing to check. I mean, if you had the positronium at rest. Now, remember, because of quantum mechanics, there's going to be some uncertainty in its position. Okay? And so there's a region in which you may have known that the positronium was in. And then the positronium decays. And if you trace it back along the world line of the photon that comes out, the 2 photons, they will intersect. Now you could draw a space-time picture of this. Here's the space-time picture. Here's the positronium. Time goes up. This is the world line of the positronium at rest. Then the positronium decays, and a photon goes out this way. Whoops, that's not very good. Photon goes out this way, and a photon goes out this way. If you trace back along the world line of the photon, you will find out that they will intersect, first of all, at the spatial location where the positronium was, but they will intersect it at exactly the same time. Or at least at the same time if we ignore quantum uncertainties.
What determines the axes along which the 2 photons come out of the positronium?
Random. Sometimes that way, sometimes that way, sometimes that way. That's the randomness of quantum mechanics. Uncertain. That's it's like taking a spin, orienting it this way, and then measuring it along the other axis. Sometimes this way, sometimes that way. So it comes out with some angular distribution, but randomly in different directions. And at random times to some extent.
When you first defined L earlier this evening.
The Lagrangian?
Right. I think you picked it because it was the one thing we had available that would be invariant.
The action principle being a statement about minimizing something or other about a trajectory will be invariant if you choose the action to be invariant. Right, so we...
Is there a more bottoms-up way to see that?
No. No. No.
So when we did the classical mechanics, I mean, I understood, I hope this is right, that we basically chose the action so that when you get the Euler equations for that path integral, that they provide the equations of motion.
Newton equations. Newton equations, yes indeed.
So, but it didn't seem like there was anything analogous going on here. Maybe
Well, no, the only reason, we haven't put anything concept of force. Now, all right, what we could do is we could take this Lagrangian and work out the equations of motion and see what the equations of motion say. But we already know what they say. They say that the energy and momentum and therefore the forward velocity is constant, and that's all they say. Just as Newton's equations, when there's no forces around, just say, well, I say that mass times acceleration is 0. That's the same as saying the time rate of change of momentum is 0, or that the momentum is constant. All right, so this will say that the momentum is constant, nothing more, or that the forward velocity is constant. Well, the forward velocity being constant, that means not only in magnitude, but in direction. It says that the particle moves along a straight line in space-time. That the motion of the particle is a straight line through space-time, and that says it moves along a line in space with constant velocity. That's the whole content of the Euler-Lagrange equations for this particular case. Now we could try putting force, we could try asking how does this get modified if we try to put various kinds of forces in, and we will do that. One of the things we will do is allow the particle to have a charge and to couple it to an electric and magnetic field and see how it moves. But so far, that's a little more complicated than anything we've done up till now. Up till now, the whole content of the Euler-Lagrange equations is just momentum and energy conservation. Or straight line motion, but not just straight line motion. Two of Newton's laws become the same law. What are Newton's laws? A particle moves along a straight line, and the other one says a particle moves with constant velocity. Here it becomes a particle moves in a straight line through space-time, which entails both straight line motion and constant velocity. One more question. Then I gotta go.
You talked about how in the limit where the velocity gets very low, that relativity, the laws approach the laws of Newton.
Right. Or at least the laws of conservation as they would have been derived from Newton. Yeah.
Right. And I'm just trying to make a connection. I'm not really sure here, but in a previous quarter we were talking about quantum mechanics. We're talking about in this other limit where you increase the mass, the laws of quantum mechanics also approach
Yes.
Newton's law.
But it's an entirely different limit.
Yeah, right. One is velocity, and the other one is like the mass or the number of particles or something?
A combination of various things, but let's say the mass of the object. And the important thing is the mass of the object and the smoothness of the forces that act on it. They shouldn't be abrupt and sudden. But that's another, we've got to separate things. This has got to do with the speed of light. Quantum mechanics has to do with Planck's constant. And you can have a situation which is highly quantum mechanical but non-relativistic. You can have a situation which is highly relativistic and not quantum mechanical. And you can have both, relativistic and quantum mechanical, the two independent limits.
Is this where they say that there's a compatibility between the two? I don't know where I read that.
No, there's no incompatibility. I think you're thinking about gravity. Gravity, there are puzzles about, but we haven't gotten there yet. So far, we're not dealing with gravity at all. We'll come to it. Okay, I think it's time to go home.
For more, please visit us at stanford.edu.